Good afternoon, students. Today we are going to discuss the magnetostatics part 5. That means the force due to the magnetic field. So let us start with the point, that is the force due to the magnetic field. So here at least three ways by which the force due to the magnetic field can be experienced. Number one, the force can be experienced by a charged particle which is moving in a magnetic field. Number two, the force can be experienced on a current element which is placed in an external magnetic field. And the third one is the force between two current elements. So one by one we are going to discuss, or we are going to elaborate these 3 points, that is point 1, 2, 3. Now the first point is the force on a charged particle. Now we have seen again that we are going to take the reference from the electrostatic, that is in electrostatic we have seen the electric force Fe. Here the subscript E represents the electrostatic field. So the force due to the electric field or electrostatic field on a stationary or moving electric charge Q in an electric field is given by the Coulomb's law, and it is related to the electric field intensity E, which is given by the expression 23.1, that is Fe equals to QE, or you can say the force due to the electric field is equals to Q into E. E is the electric field intensity. Now in this expression 23.1 you can see that the Q is positive. So we can say the force due to the electric field and the electric field intensity is in the same direction. Now here, but in the case of magnetic field, the magnetic field can exert force only on a moving charge. So in the case of electrostatic, what we have seen, that if the charged particle is at rest or it is moving in an electrostatic field, the charged particle will experience the force due to the electrostatic field. But in the case of magnetostatic field, the charge must be moving. So when the charge is moving, then due to the magnetic field, the charged particle will experience the magnet force due to the magnetic field. Now it is found from the experiments that the magnetic force Fm, the force Fm experienced by a charge Q which is moving with a velocity u in an external magnetic field B by that expression 23.2, that is Fm equals to Qu cross B. And here from this experiment or from this equation you can see that this Fm is perpendicular to both the velocity u and the external magnetic field B. Now from equation 23.1, that means here 23.1 F equals to QE, or and 23.2 we can compare that, we can have the comparison between the electric force Fe and the magnetic force Fm. The first comparison we can say that Fe, here Fe is independent of the velocity of the charge and can perform work on the charge and can change its kinetic energy. So here you can see that this Fe equals to QE. Here no velocity is showing here in this expression. So we can say that Fe is independent of the velocity of the charged particle. However, the force Fm if you can see that in 23.2, Fm cannot perform work because it is at the right angles to the direction of the motion of the charge. Here the Fm is perpendicular to the velocity of the charge particle. That is why that Fm dot dl will be equals to 0. So obviously it does not increase the kinetic energy of the charge. So now for a moving charge q, if we consider a situation that where the moving charge q is present or moving charge q is placed in both the electric and magnetic fields, the total force will be the summation of the force due to the electric field plus force due to the magnetic field. So the total force F will be equals to Fe plus Fm. We have seen that Fe equals to QE, so we are replacing this Fe by QE plus Fm is replaced by Q U cross B. Now if we take the common of this Q, then F equals to Q within bracket E plus U cross B. So this equation 23.3 is known as the Lorentz force or Lorentz force equation. Now it is interesting to see that this Lorentz force can be related, or we can relate the Lorentz force with the Newtonian force. We know the Newtonian force, if the mass of a charge particle moving in an electric field and the magnetic field having the mass m, by Newton's law we can write F equals to m du dt. So this m du dt will be that this force, equation 23.4, this force F, and equation 23.3, this force will be equal. So we can write m du dt equals to QE plus Q U cross B. Now if we solve this equation 23.4, we can find out the velocity of the charge particle u if the mass, the external electric field E, and the external magnetic field B is known. So in this way we can relate the mechanical force with the electronic or electrostatic force. Now also we should remember that in this kind of fields the energy can be transferred only by means of the electrostatic field or the electric field, not by the magnetic field. Now the second point, that is the force on a current element. Now to find out the force on a current element, here the current element we are considering IDL. Here you can consider a current carrying conductor. This current carrying conductor is having the current flow is I, and if we consider a small length dl, so the current element can be written as IDL, here IDL. So the current element IDL of the current carrying conductor due to the magnetic field, here the magnetic field is external magnetic field. So the current carrying conductor is placed in an external magnetic field. If we place the current carrying conductor in an external magnetic field, then that current carrying conductor will experience a force due to the magnetic field, and that can be written using the fact that the convection current J equals to rho V into U. In the earlier lectures we have seen that the convection current density J equals to rho V into U. That equation we are going to use. Now another point we should know that the current element for the line current is ideal, which will be equivalent to the KDS. Here KDS is the surface current element equivalent to the JdV, that is the volume current element. So all these current elements can be taken as the equivalent current. Now this IDL can be written as IDL equals to JdV. Here J is replaced by rho V into U. So rho V into U into dV. Now rho V into dV is the dq charge which we can have within the current element or the elemental length dl. So I dl can be written as dq into u. In other way, we can get that expression that I dl is equals to dq into u. How? You see that alternatively we can write that I, that current, the definition according to the definition of the current I, that is equals to dq dt. Now, if we multiply in both the side of this equation by dl, so it will be ideal, that will be equals to dq dt into dl. Now, keeping dq as it is, dl by dt means the change in the length by time, change in the time. So that is the velocity. So here you see that we have ultimately I dl equals to dq into u. So we can write that equation 23.7, that is I dl equals to dq into u. Now this equation shows that the elemental charge dq moving with the velocity u, thereby producing the convection current element dq into u is equivalent to the conduction current element idl. So this equation 23.7 is very much important, which shows the relationship between the convection current density or the convection current with the conduction current. Now here therefore we can say the force on a current element ideal placed in a magnetic field B is found from equation 23.2. That means from this expression, just if we take the derivative of this Fm, that is dFm equals to dq into u cross B. So here you can see that again that df equals to ideal cross B, because df equals to dq into u. So dq u is replaced by ideal cross B. So that expression is the force of on the current element due to the external magnetic field B. Now if we want to calculate the force on a current carrying conductor which is closed, that means a closed current, or we can say if the current I flows through a closed path L or a closed circuit, the force on that circuit is given by F, that means the integration of this equation 23.8, that is F equals to closed line integral I dl cross B. Now using this expression 23.8 and 23.9, we should keep in mind that the magnetic field produced by the current element ideal does not exert force on the current element itself. Just as the point charge we have seen in the case of the electrostatic, a point charge does not exert force on that particular point charge, but this in the same way we can say that the current element does not exert force on the element itself but the force exerted on this current element due to the external magnetic field B. So here that is written, the B field that exert force on ideal must be due to the another element, that means the external magnetic field. Or in other words we can say the B field or the magnetic field in equation 23.8 and 23.9 is external to the current element ideal. Just we have discussed this one. Now if instead of considering this current element, the line current element ideal, we have the surface current element KDS. We have seen earlier that ideal is equivalent to KDS. So we can, if we replace this one, we can find out the force on the surface current element due to the external field, that is written in the expression. You can see that dF equals to KDL cross B. In the same way, we can calculate the force on the volume current element, that is KDL is replaced by JdV, that is dF equals to JdV cross B. So in this way we can find out the force on the current element due to the external magnetic field. And another point I want to mention here, that the current element can be the line current element, the surface current element, the volume current element. So here that dF, here in this equation 23.10, you can see that the dF equals to KdL, K dl cross B. So force we can find out using the integration, that is F equals to surface integral of KdL, KdS cross B, and here volume integration, that is F equals to volume integration J dV cross B. Here one point I have missed, that here this KdL will be replaced, this dl will be ds. It is wrongly printed that KdL, but it will be KdS. Here F equals to surface integral of KdS cross B, and for the volume current element F equals to volume integral of J dV cross B. Another point I want to mention here, that the magnetic field is defined as the force per unit current element. Just like we have seen in the case of electrostatic, that force F equals to QE. So if the force is divided by Q, we have the electrostatic field intensity F by Q, that is the electrostatic field intensity. Similarly, we can find out the magnetostatic field intensity, that is Fm by Q. So here Fm by Q equals to U cross B. Here you can replace this small q by the capital Q, which we have seen in the earlier cases, that Fm cross B, Fm cross B equals to U cross B, just as we have defined the electric field E, that is F E by Q. Now both these definitions of B shows that B describes the force properties of the magnetic field. So this is the discussion about the second point, that is the force on a current element due to the external magnetic field. Now the third point we are moving, that is the force between the two current elements. Here in the right side you can see the current element, that is the current loop 1, and in this current loop the current is flowing in the anti-clockwise direction, and here we have considered a very small length dl or dl1 because it is the loop 1, and the current is flowing is I1. So the current element we can consider I1 dl1 dl1 or di1 idi1. Similarly, the second current loop, the current is flowing in the clockwise direction and the current flowing is I2, and the small length we are considering dl2. So the current element for the loop 2 will be I2 di2 or dl2. Now according to the Biot-Savart's law, we can find out the force on the current element I di1 due to the magnetic field produced by the loop 2. I repeat, the force on I1 d1, that means the current element 1, due to the magnetic field which is produced by the current loop 2, that can be written as d of df1. So d of df1, that the force d of df1 on the element I1 di1 due to the magnetic field db2. Here db2 is produced by the current element I2 di2 of the loop 2. So here we can write d of df1 equals to I1 di1 cross db2. Here db2 is the external magnetic field which is produced by the loop 2. Now using the Biot-Savart's law, we know that the magnetic flux density or magnetic field intensity, you can say magnetic flux density dB2 equals to mu naught I2 di2 cross AR21. Here AR21 is the unit normal vector from the current element I2 di2 by 4 pi R21 square. Now if we place dB2 in this expression 23.12, we have the expression d of df1 equals to mu naught I1 d1 cross I2 d2 cross AR21 by 4 pi R2 square. Now, if we take the double integration of this equation 23.14, we have that F1 equals to, here mu naught is a constant, the current we can consider is a constant, I1, current 2, I2 is constant. So, taking this I1, I2 outside the integration by 4 pi, this is also constant. So, line integral 2 times di1 cross di2 cross ar21 by r21 square. So, what we have seen that force on that current element or the current loop, force on that current loop F can be expressed due to the external magnetic field produced by the current loop 2 can be written by the expression 23.15. It looks very complex, but it will be easier if you study it step by step. So, that is the force. Now, here equation 23.11, we are using that expression only to find out the force, or 23.12, that two equations 23.11 or 23.12, 23.12, that means this equation is the fundamental equation to find out the force due to the magnetic field. Similarly, we can find, if we want to consider the case 2, that is the force on the current element I2 di2 due to the magnetic field produced by the current loop 1, that will be the just the opposite of the force F1. So, F2 will be equals to minus of F1, and if we change the subscript in the expression 23.15, if we only change the subscript, we can have the expression of F2. So, here F2 equals to mu naught I1 I2 by 4 pi integration, double integration di2 cross di1 cross ar12 by r12 square. So, in this way we can find out the force on a current element, or the first one you can consider the force on a point charge which is moving in an external magnetic field, or the second case, that is the force on a current element or current carrying conductor which is placed in the external magnetic field, or we can find out the force between two current carrying conductors which uh, in which we can consider the force F1 due to the magnetic field of the loop 2, or F2 due to the magnetic field of loop 1. So, that is all for the today's class, students. In the next class, we will move to the boundary conditions due to the magnetic field. Thank you very much. That is all for today's class.